Hi, welcome to the Signal Path. This episode is all about analog circuit design. Specifically, I wanted to show you how a deceptively simple single-stage amplifier can actually be quite difficult to design. And I wanted to show you how much thought and design consideration goes into making a very simple amplifier. So I'm going to introduce a particular application, then we're going to design a single-stage bipolar amplifier from the ground up, and then we're going to build that circuit and then measure it so we can compare our measurements based on what we've done in theory. So the purpose here is to create a bridge and show you the experimental and theoretical work go hand in hand, and to kind of give you a little bit of an understanding of a very basic amplifier design. And for those of you who are taking introductory analog electronics or intermediate analog electronics, this should hopefully serve well for your coursework as well. So let's get started. So I have prepared some notes with regards to the spec and the design of the amplifier, and I will make these notes available to you on the website later on so you can look at them at your own time. So let's go over the design and spec of the amplifier. So as I mentioned, we want to use this audio amplifier to amplify the signal from a microphone such that it becomes large enough that can be processed by, let's say, an analog to digital converter. Now a microphone, an inexpensive microphone, is not going to give you more than about 10 millivolt peak to peak or so. So if we design our amplifier to have a gain of 1,000, a gain of 100, then we're going to get about 1 volt peak to peak coming out of the amplifier, which would be good enough for an analog to digital converter. We also want the bandwidth of the amplifier to be at least 20 kilohertz. We don't want it to be too high, because anything more than 20 kilohertz a human ear can't hear anyway. So it's just going to be noise in the system, so we may as well filter it out. But we want to have at least 20 kilohertz of bandwidth so that it covers the entire audio range. Here I've also chosen the power supply to be a complementary plus or minus 2.5 volt, but you can design it to be a single, let's say 5 volt supply as well, it's not a problem. And I want to minimize the power consumption to be less than 50 milliwatt. So with this spec, we can choose an amplifier and start designing it. Now you may say, well, I can just use an op-amp and put it in feedback and set the gain to be 100 and I'll be done. You could, except that an op-amp, unless you buy a very good one, an expensive one, is going to have a lot of noise. A very low noise op-amp can be quite expensive. But if I were to use a single stage bipolar amplifier, it's going to have very little noise, it's going to be significantly cheaper, and plus we get to design it. So for our purposes, I've chosen a common-emitter amplifier, which is going to use a single NPN device. Now I'm using a 2N2222A type NPN device, which is very common, and I have looked at this data sheet, and it provides a beta of 100, that's this current gain, and it gives you a base emitter, saturated base emitter voltage of 0.6 volts. So when it's forward biased, this base emitter junction voltage will be 0.6 volts, and its saturated common emitter voltage is 0.2 volts, which means that if you make a common emitter, collector emitter voltage smaller than 0.2 volts, then the device is saturated, it's not good for an amplifier anymore. Now, with these three parameters, the base emitter voltage, the collector to emitter saturation voltage, and the beta, with these three information is sufficient for us to go ahead with the design of the amplifier. We can also make some assumptions. Let's assume that beta is equal to beta plus 1, just to make our calculations easier, which means that the collector current and the emitter current will therefore be the same. Usually the collector and emitter current are different by a factor of beta over beta plus 1, but since we're assuming that they're equal, we can simplify our calculations. So here I've reproduced the schematic of a very basic common-emitter amplifier. Here I'm showing the DC operating point. Now, what does that mean? With this schematic here, we are able to design the DC operating point of the amplifier, which is its bias current and all the voltage distributions between all of its components. If we don't do this step properly, if we don't choose a correct DC operating point, then the small signal or the SE behavior of the amplifier is going to be very poor. Most of the design is concentrated at this stage. So by going through a KCL loop starting from the base voltage, the base resistance, and the emitter resistance, I can write a loop in this path that's going to give us the DC operating point. Now I will explain why I have chosen the emitter resistance here at a later point. So starting from VB, we have the base current going into the NPN device, so we have VB minus the base current times the base resistance. Then we have the base emitter junction voltage, so minus VBE. Then we have the voltage drop across the emitter resistance, which is the emitter current times the resistance, that's IERE. And then we end up with the negative power supply minus 2.5 volts. So this equation therefore, can be used to find a DC operating point. Now, if I take advantage of the fact that I know the relationship between IB and IE, that's just a factor of beta, I can rewrite this equation and solve for the emitter current, end up to be this equation. Now, let's take a look at this equation for a moment because there's a lot of information in it that's important. So here the emitter current depends on the bias voltage VB. That makes sense because that's the bias voltage of the device. We apply this, so this is in our control. Plus 2.5 volts, again, that's our power supply. That makes sense. The base emitter junction, that's the property of the transistor. We know that. That also makes sense. Then we have the base resistance, which we've added, divided by beta, plus RE. Well, this equation will work just fine if I set RE equal to 0. In fact, I can set RE equal to 0 and not have an emitter resistance at all. But then let's look at what happens. If I set RE equal to 0, then this equation is going to be directly a linear function of beta because this beta is going to come to the top, it's going to get multiplied here. So if RE is equal to 0, then IE will be a direct function of beta. That's not a good thing because beta is a variable, is a device parameter that changes from one device to another. So if you were to build one and you calculate everything and use a beta of 100, next time you get another device, the beta could be 75 or the beta could be even 200. So the high variation in beta means that we have to have an emitter resistance here because by making this RE large enough, we desynthesize the biasing of the amplifier to beta. So you can think about it that in this denominator, if RE is much larger than RB divided by beta, then this doesn't matter at all. Then your biasing is a strong function of RE and not a strong function of beta. This is very important in case there is beta variation. So that's why we have added this RE here. So we have this equation, but this equation doesn't really allow us to solve for any of the values RE or RB. We don't know what those values can be. There's too much freedom. So we need to take other things into consideration. So now that we took the beta-insensitive biasing into consideration, now we can take a look at signal swing. Because depending on the DC operating point that we chose for our amplifier, its output signal swing is going to be affected. So let's look at this amplifier again. The output is taken from the collector since this is a common-emitter amplifier, and the input will be applied to the base, but I haven't shown that here. Now let's see how will the output signal swing be affected by the way we distribute the voltage along these devices. So the output voltage is going to swing up and down as I have shown here. Now the highest voltage it can reach is the positive power supply because we cannot go over the positive power supply. If this voltage reaches 2.5 volts, then the device is already turned off because there will be no current through the device at all if the voltage across this resistor ends up being 0. So the signal can go as high as 2.5 volts, and how much swing it has will depend on how much voltage we have across this resistor. So the more voltage I put across RC, the higher swing I have at the upper side. But what about the lower side? Well, on the lower side, this voltage is going to go lower, lower, and lower until the device reaches this collector-emitter saturation. So as I swing lower and lower, as soon as the voltage between the collector-emitter of this transistor here ends up being VCE sat, which we know is 0.2 volts, this device is going to go out of its active region of operation, and it's not going to make a very good amplifier anymore. It's going to be highly nonlinear. So, therefore, how much swing I can have on the low side is the voltage I have dedicated to the collector-emitter voltage across the transistor minus its collector-emitter saturation voltage, which is 0.2 volts. So we can see right away that how much swing we can get from this amplifier is a function of how we distribute voltage across this resistor, this transistor, and this resistor. And from a previous stage, from the previous discussion we had about biasing, we know that we need RE, so now we have to think about how we're going to distribute this. So to reiterate what I said, the positive signal swing is the voltage across the resistor, the collector resistor. The negative voltage swing is the collector to emitter voltage minus 0.2 volts. So we want to make these as large as possible because we want to have as much swing as possible. So now that we took the beta-insensitive biasing into consideration, now we can take a look at signal swing. Because depending on the DC operating point that we chose for our amplifier, its output signal swing is going to be affected. So let's look at this amplifier again. The output is taken from the collector since this is a common-emitter amplifier, and the input will be applied to the base, but I haven't shown that here. Now let's see how will the output signal swing be affected by the way we distribute the voltage along these devices. So the output voltage is going to swing up and down as I've shown here. Now the highest voltage it can reach is the positive power supply, because we cannot go over the positive power supply. If this voltage reaches 2.5 volts, the device is already turned off because there will be no current through the device at all if the voltage across this resistor ends up being 0. So the signal can go as high as 2.5 volts, and how much swing it has will depend on how much voltage we have across this resistor. So the more voltage I put across RC, the higher swing I have at the upper side. But what about the lower side? Well, on the lower side, this voltage is going to go lower, lower, and lower until the device reaches this collector-emitter saturation. So as I swing lower and lower, as soon as the voltage between the collector-emitter of this transistor here ends up being VCE sat, which we know is 0.2 volts, this device is going to go out of its active region of operation, and it's not going to make a very good amplifier anymore. It's going to be highly nonlinear. So, therefore, how much swing I can have on the low side is the voltage I have dedicated to the collector-emitter voltage across the transistor minus its collector-emitter saturation voltage, which is 0.2 volts. So we can see right away that how much swing we can get from this amplifier is a function of how we distribute voltage across this resistor, this transistor, and this resistor. And from a previous stage, from the previous discussion we had about biasing, we know that we need RE, so now we have to think about how we're going to distribute this. So to reiterate what I said, the positive signal swing is the voltage across the resistor, the collector resistor. The negative voltage swing is the collector to emitter voltage minus 0.2 volts. So we want to make these as large as possible because we want to have as much swing as possible. So let's combine everything that we have discussed so far. Based on our discussion on signal swing, we want the voltage across the resistor in the collector to be equal to the voltage swing of the collector emitter minus VCE sat. So this is the swing at the bottom, it's the swing at the top, and then we also have the voltage across the resistor in the emitter. So let me go back to this paper again. So if I want to maximize this voltage, and this voltage at the same time, one solution is to make them all the same, because that will make them all equal and that will make them all the maximum they can be. But of course, this voltage plus this voltage plus this voltage cannot be large indefinitely because we have a power supply limitation. Therefore, we know that the voltage across the resistor in the collector plus the voltage across the collector emitter in the transistor plus the voltage across the resistor in the emitter has to equal to 5 volts. That is our signal swing. We have our signal swing and our biasing taken all into account. Now, since I know that they have to sum up to 5 volts, I can solve these two equations simultaneously, and that tells me that I have to distribute my 5 volt power supply between the resistor in the collector, between the resistor in the emitter, and the transistor itself. It may sound obvious, but we now know exactly how we need to distribute our voltages in order to get the most from our biasing as well as the most from our signal swing. So based on everything I've said so far, all we've done is we've only narrowed down the resistor in the collector to be equal to the resistor in the emitter. Now, this is the first time we actually have a restriction on our components. So now that I know that these two resistors are the same, we can go ahead and start looking into small signal gain. So how does this amplifier behave in small signal mode? I will apply my input to the base, and I'm taking the output from the collector, and I have my resistors in the collector and in the emitter. So if you were to go through the small signal calculation, I'm not going to go into the detail of that. The gain of this amplifier is minus GM divided by 1 plus GM RE times RC. That's because the resistance in the emitter acts as a degeneration resistor, which lowers the effective GM. This is our effective GM. So if the value of GM RE is large enough, then this can be simplified to minus RC over RE, which is minus 1. Well, that's not much of an amplifier at all. It means that if I add RE, the gain of this amplifier is just going to be minus 1, because we know that RC and RE have to be the same. So this is not amplifying anything. In fact, it's essentially worse than just a wire. But we need RE because we want to make sure the biasing is insensitive to beta. But we also don't want RE because with the RE, our gain is only minus 1. So we need a way of having RE at DC but not having it at AC. Well, of course, we can just add a capacitor and solve that problem altogether. So let's take a look here. If I were to add a capacitor CE in parallel with RE, this capacitor is not there at DC, and I have my beta-insensitive biasing without any problems. But at AC, if the value of CE is large enough, then this is going to act like a short circuit and it's going to eliminate RE altogether. In that case, our small signal gain is just going to now become minus GMRC, which is equivalent of setting RE equal to 0 in this equation. So we also know that GM is IC over VT. So if I write the whole thing out, I get minus IC over VT times RC. But guess what? The product of IC and RC is just a voltage across RC. But from a previous equation, when we were talking about our linearity, we already calculated what the voltage across the resistor in the collector should be. The collector resistance voltage across it should be 1.6 volts. That's the product of IC times RC. So I already know what that is. And I can put the product of these two to be equal to 1.6, and VT is 25 millivolt at room temperature, which 1 over 25 millivolt is 40. So 1.6 times 40 is minus 64 volts per volt. Now, this is interesting because I don't even know what the current in this device is. I don't even know what the value of RE and RC are. I haven't set any of these values, but I know what the gain of the amplifier has to be, and I know I cannot get more than this under the linearity and biasing conditions that I have set before. So this is, to me, a very interesting result because I know no matter how much current I put in this, no matter what I do, I can never get more than 64 volts per volt because of my linearity and biasing constraint. So I already know the gain of the amplifier. Now we need to find reasonable values for RE, RC, which we know should be the same, and for CE, and we need to finalize the design of the amplifier. And here's the schematic of our complete amplifier. Let's see what we have. We have our input signal. This is going to come from the microphone. Now I have a series capacitor here because I don't want to interfere with the biasing of my amplifier. I want to have a decoupling between the biasing or the DC voltage that is coming from Vin and the DC voltage that I have in my amplifier. So I'm using a series capacitor to isolate them. Now I'm using the resistive divider RB1 and RB2 in order to create the base voltage that I need to get my biasing. Again, we discussed this before. And I have my collector resistance, my emitter resistance, and I have my collector capacitance, my emitter capacitance here in order to shunt the resistor in the emitter to get the large small signal gain. And I have added a collector capacitance to limit the bandwidth of the whole thing to be about 20 kilohertz. Now, I don't have any actual value limitation on what the collector current should be. I can choose anything I want. Here I've chosen 2 milliamps. In reality, there is some noise biasing consideration that's going to actually give you an optimal collector current, but we're not going to get into that. I've just chosen 2 milliamp as a good value to start with. So if I set my collector current to be 2 milliamp, I can solve for all the other variables. Therefore, my RC and RE should be 800 ohms. My RB1 and my RB2 should be 14 kilo ohm and 10 kilo ohm respectively to get the voltage that I need on my base. And I have set the collector capacitor to be 10 nanofarad so that I will get a bandwidth of 20 kilohertz. But what about the value for CB and CE? Well, you can choose them to be as large as you can make them because these guys will determine your low frequency cutoff bandwidth. Because remember, these capacitors are going to be open at low frequency. So if this capacitor is open at low frequency, your Vin isn't going to even get into the device to begin with. So therefore, you're going to get no gain at all. You're going to get a gain of 0 at DC. So, but it doesn't matter so much because the human ear can't hear less than about 50 hertz anyway. So if you can choose the value of CB and CE to get your low bandwidth cutoff to be about 50 hertz, and I'm going to leave that to you to figure out what that value should be. So with this, we're going to get our complete single-stage common-emitter bipolar amplifier. But we have a small problem. We wanted our gain to be 100, but we calculated that the gain of this amplifier cannot be more than 64. In fact, the gain of this amplifier is about minus 64 volts per volt. So therefore, this needs a second stage. Since we already have most of our gain in the first stage, we can add an op-amp as a second stage because the noise of the op-amp at that point is not so important anymore. We have already preserved our signal-to-noise ratio because we have most of our gain here in the front. And in order to do that, we're going to do something very simple. We're going to take our amplifier, this is our amplifier, common-emitter amplifier, and we're going to connect that to a simple non-inverting op-amp configuration with the value of the resistors to be exactly the same, and the gain of this stage is just 1 plus R over R, which is 2. So 2 times 64, that's 128, so we'll have a gain of about 128. Now there's some details that I haven't discussed here. For example, you have to AC couple your amplifier from the next stage and so on, so I haven't discussed that, but I'm going to leave the rest of it to you, and I'm going to upload all these pages to the website so you can download and look at them. But let's get to some of the more fun stuff. Let's build and measure the circuit. Alright, here we go. I have built this circuit that we discussed. Let me show you a close-up so I can describe to what I have. So here I have both stages of the amplifier, the op-amp and the bipolar common-emitter amplifier, both of them assembled on the breadboard. So at the left side, let me get a bit of grip on this. Here we go. So the input is currently coming from this BNC connector. Right now we're going to first test this using a signal generator before we test it using an op-amp. So here is the input capacitor that decouples the signal generator from our amplifier. Here's our bipolar device right here. Here's our collector resistor and the capacitor that limits the bandwidth to 20 kilohertz. This guy is the series capacitance to the next stage. We'll talk about it after. And here's our shunt capacitor across the emitter resistor here. So the emitter resistor, the collector resistor, the transistor, and the bias resistors are here and here. I'm using a little potentiometer here because I didn't have exactly the value of the resistance that I wanted, so I'm just adjusting it based on what I need. And here's our second stage amplifier, which is just an op-amp in feedback with 2 equal resistors, and this is a offset cancellation resistor that I have added, which is not in the schematic. And I have 4 large decoupling capacitors to reduce the noise on the breadboard. So the input signal is going to come from here, is going to go through the series capacitor, is going to be applied to the bipolar transistor. The output is taken from the collector, goes through this capacitor, is applied to the input of the non-inverting op-amp, and then the output is taken from this guy. So I can look at the output of the op-amp here, and I can look at the output of the common-emitter amplifier here, and this is just a ground signal. So let's hook it up and first measure our DC operating point, which I mentioned is the most important thing. So in order to do that, I am going to use my Regal DP1308A power supply. I'm going to set to this power supply to plus or minus 2.5 volts. It's easy enough. 2.5 volts here and 2.5 volts here. So now I have plus 2.5 and minus 2.5, and I can turn everything on. It's asking me if I'm sure about that, and I say yes, and it's turned on and it's applying plus or minus 2.5 volts. Here we go. So now I can go ahead and actually measure all the voltage that I'm supposed to be reading. So in order to just be able to, hopefully you can see this, put it somewhere that's more visible. There we go. So I'm going to measure all the voltages. So based on our discussion before, what are we expecting? We are expecting the following. We want the voltage across both of our resistors to be 1.6 volts, and we want the voltage across the device to be 1.8 volts. So close to those values is what we've designed for. With these values, we should be getting roughly the gain that we expect. So let's measure that. I'm going to measure the voltage across the emitter resistance. There you go, 1.64. We designed for 1.6. It's pretty good. The voltage across the collector resistor, again 1.64, no problem. The voltage across the collector emitter of the device, 1.7 volts. We've designed for 1.8. It's close enough. And the voltage on the base of the device itself, which is here. base voltage is minus 0.2 volts. It should be about minus 0.3, but it's pretty close. So, and of course my plus and minus 2.5 volt supplies should be correct. There you go, that's plus 5 volts, that's between the two power supplies. So everything checks out. The DC operating point of the amplifier is actually correct. So now that we know that this is correct, we should be able to go ahead and apply a signal and actually measure the output. So move this. Now let's set up our signal source. So since this is in the audio range, we can set it to about, let's say, 2.5 kilohertz. That's a reasonable value. Now we know the gain of the amplifier should be about 100, 120, let's say 128 is the maximum we are expecting to get. So what I want to do is I want to make sure I apply a signal that's small enough that doesn't saturate my amplifier. So let's say I can apply about 5 millivolts. Now I have terminated the output of the signal source. So I'm going to tell the signal source that its output impedance is 50 ohms, like so. That takes care of that. And I can set its amplitude to be 5 millivolt peak to peak, which is in fact actually the smallest I can get from this signal generator. So I will go ahead and enable the output. So now it's applying 5 millivolt peak to peak sinusoid at 2.5 kilohertz to our circuit. Now we can just back a little bit. Here's the circuit, here's the oscilloscope. We'll connect this up. There we go. And I will look at the output of just the first stage. There it is. Now let's see if this makes sense. I am applying a 2.5 kilohertz signal, so let's look at the oscilloscope more carefully. So what am I seeing? I'm seeing a sinusoid that has a frequency, I'm measuring it here, 2.5 kilohertz. It also shows up here at the top in the frequency counter, and it's obviously a sinusoid. It looks nice, doesn't seem distorted, and its output amplitude is 294 millivolt peak to peak. So I'm applying 5 millivolt peak to peak. I'm getting approximately 300. So that's a gain of about 60, just under 60. Now it's not 64, and the reason is because there is some extra loading in there that I'm not talking about specifically in the schematic, but it's really close to what we calculated. And if I go to the output of the op-amp, right now I'm looking at the output of the bipolar device itself. The output of the op-amp is here. I expect the output of the op-amp to be twice as big, to have a gain of approximately about a gain of 2 or so. So I'm going to take a look at that. There we go. I'm getting about 515. It's a little bit less than that. I suspect one of the reasons is because one of the resistors I'm using might not be very good up to spec. But it's pretty close. We're getting about 515 millivolt peak to peak, and if I divide that by 5, I get just over 100. So we have met our gain requirement. We have just over 100 volts per volts gain from both of the amplifiers combined. So let's measure the high frequency bandwidth to see if our calculation matches our measurement. So based on the calculation, we should have 20 kilohertz of bandwidth. The 3 dB bandwidth should be 20 kilohertz. So what's the easiest way to measure that? Well, the easiest way to measure that is to look at the gain that we have right now. The gain that we have right now is about 500, let's say 520 millivolt. So if it's 520 millivolt peak to peak is our output signal swing, at the 3 dB point, we will have 520 millivolt peak to peak divided by the square root of 2. Now what is that equal to? I can get my calculator. So 520 divided by the square root of 2, that is 367. So I can increase the frequency until my output swing hits 367 millivolt peak to peak. At that point, I have lost a square root 2 factor of the output voltage swing, which will correspond to 3 dB reduction in the output gain. So let's do that. Let's increase it until we hit that point. So right now I'm at 2.5 kilohertz. So I'm going to go to 10.5 kilohertz. It's still okay. we have now had a little bit of a reduction. Now we're at 472, but we haven't hit 367 yet. So we're going to keep increasing it. This is now 11 kilohertz. Say 16 kilohertz. No, not yet. 20 kilohertz. Oh, 378. We're really close to that. And a little bit more. There. 300, and it's just under 367. So it's more like here I should be looking at. There it is, 368. Perfect. So at this point, I have lost 3 dB gain. And what is the frequency? You could read it on the oscilloscope also, but it is 21.5 kilohertz. So at 21.5 kilohertz, which you can see also here, we have hit our 3 dB bandwidth. So anything higher than this is going to continue to be attenuated at a 20 dB per decade range. So I can increase the frequency. You can see it's getting smaller and smaller and smaller as I'm attenuating the signal. Now I'm at 60 kilohertz, and it's already been reduced significantly. It's only at 181 millivolts. So if I go back to 2.5 kilohertz, I will get my full gain again, 525 or so millivolt peak to peak, which corresponds to just over 100. So we have essentially met our specification. We have a two-stage amplifier that's reasonably low noise, which, although I'm not measuring the noise here, but it has a gain of over 100. Its power consumption was supposed to be less than 50 milliwatt. Now together, combined, I have 20 milliwatt from one power supply and 20 milliwatt from the other power supply. It's 40 milliwatts, so we're less than 50 milliwatts, so we've met that. So we have met all of our requirements for this amplifier. Now the only thing to test is that can it amplify an audio signal. So I'm going to add a microphone to it. Alright, I added a simple microphone, and I've biased the microphone from the same power supplies that are used to power the entire amplifier chain, and I have connected the output of our little microphone directly to the bipolar input. So the signal from the microphone goes through the bipolar, through the op-amp, and into to the oscilloscope. So I will now show you that. Here you go. This is the output of the oscilloscope. So you can see as I'm speaking, it's picking up the audio signal and it's amplifying it. You can see the time waveform there. So if I whistle, you can see that it is in fact doing a very good job at amplifying it. So now you can see this is on a 200 millivolt peak-to-peak signal, and I am easily getting signals that are almost 1 volt peak-to-peak from this amplifier chain. So I can connect that directly to an analog to digital converter, and then I will be able to get the signal digitized and then processed and so on. Or I can connect it to a high power amplifier and drive a speaker, and I can have some kind of a very basic intercom or a telephone system set up. So I hope you enjoyed our little amplifier experiment, and I hope that you go ahead and replicate this, or you download the PDF of all of the analysis that we did earlier, so you can go over them, and you can go ahead and make modifications or design a different amplifier and then repeat this experiment. So until next time.